All right, so let's start the second day of our workshop, the second session. So Przemek, if you are ready, the Zoom is yours and we can start.
Okay, thanks, Pavel. So, hello, guys. Today we are going to talk about the quantum operators. Then we will move on to some programming session in Circ. And at the very end, we will talk about Bloch sphere. So, let's start without a delay. So, during QBronze, you learned a few gates. So the simplest one, I believe, identity gate, which basically does not change anything, but is useful in notation. You also learned about X gate, also known as NOT gate. And it basically, if you have one qubit, then it changes the first amplitude with the second amplitude. So I believe it's one of the Pauli gates, one of the Pauli matrices, so it's quite simple. Another one, which we will investigate further today, is the Z gate. And it does not change the probability of getting 0 or 1 when measuring, but it changes the local phase. Because here we have 1, so it kind of differs from the identity gate. And of course, we also learned about the Hadamard gate, which introduces superposition. And I believe you should also remember the RY gate, so rotation about the y-axis, but we will come to that later. So what I want to start with is to try to guess or make an exercise where we will try to predict for what qubit, for what vector, if we apply a given gate, then the state will not change. And particularly, I would also like to know what will happen to the local phase if anything changes. Okay, so let's start with the X gate. And to begin with, I will draw our favorite circles, where we will have the real part of the local phase, and on the y-axis we will have the imaginary part of the local phase. And of course, we will have here a complex unit circle. Maybe it does not look like a circle, but just more or less it looks like a circle. And of course, the second part of the diagram, where we will plot the amplitudes that corresponds to the probabilities of measuring states 0 and 1, and it will be a quarter of a circle. And I want to guess if we apply X gate here, so maybe I will draw here a line to separate those parts of one node. I have an X gate, and I want to guess how my qubit, how my vector should look like. So if I apply the X gate, nothing will change. And as you can remember, if you had a state ket0 and you apply X gate to it, then you will receive state ket1 and vice versa. So my guess is to place this vector somewhere there, because it will be kind of reflection around this axis. And here we will have an angle of pi divided by 4. Because here this quarter circle is like pi divided by 2, and in the middle there's a pi divided by 4. So in other words, we can interpret the X gate as a reflection around this axis, around maybe this the axis created by this vector here. So, but we also have the other circle where there is a local phase, and one thing I can, and here I would like to deduct where I should draw here a straight line or maybe a point. Okay, so let's investigate it in a more mathematical way. So we have an x gate 0, 1, 1, 0, and here let's have a state. We will have alpha and beta. However, I would like to be more direct when it comes to knowing the local phase. So I will here write something like this. I will put here some lambda, and here I will put some mu. Okay, and now I would like on the side express this vector in another way. So we will have the local phase only by beta. So in other words, I can express this vector, this qubit, in such a way where I will get this local phase by alpha part out of the vector, so e to the power of lambda. And here I will be left with, of course, beta, and here we need to divide the local phase of beta by the local phase of alpha, so we'll do the division, but because we have the exponentiation, instead of dividing, we have an subtraction. So we will have something like this, okay? Minus lambda. Okay. So now let's apply the x gate. So we will get here a vector. So it's 0 times the first part, it will be 0 plus 1 times the second part. However, we can look straight here. So we will have, let's say, it less complicated in the future. So we will have here e to the power of I times mu minus lambda. And of course, beta here. And here we will have only lambda. Yeah, so I'm like referring those two vectors are equal. Yeah. So, pardon. So here you have a global phase. Yeah. And I would like to see what changes between those two vectors. Yeah. So what here changes? Of course, alpha and beta are shifted here, but we can also see that if we, oops, I have some problems with mouse. Okay, that those two local phases seems here to be identical. And okay, and now if I want to move this local phase here, so to have it at the second part of the state vector. So I want this local phase to be near alpha now. So now I need to divide both parts of the vector by the local phase that stands by beta state. So I will have something like this. So I to the power of mu minus lambda. times, here we have beta, okay, a bit more space, and here we have alpha, but this time, because we again have 1 divided by something, we will have here a minus sign, yeah? And this minus tells us that we are rotating in the opposite direction. So usually we were where we were interpreting this local phase, we were rotating counterclockwise, so in that direction. But because we have here minus sign, we will now rotate clockwise. And that's exactly what this minus tells us, yeah? And in other words, it means that we are still rotating around this axis, yeah? And it tells us that the X gate performs a reflection or a rotation by 180 degrees around this axis. So since we need like more dimensions, we need 2 plots to do this. And here is the part that contributes for the probabilities. Here is the local phase. So if we have a state, let's say from this plot, it will be like cosine pi divided by 4, and here sine divided by 4. And when it comes to local phase, because we also need to care about this, here we need to have, here is e to the like 0th power, so it will be like 1. So here we need to have 1, or we need to be here, so on the opposite side of this reflection line. Yes, here and or here, and here is e to the power of I times pi, which is equal to -1. Okay, so here we need to have 1 or -1, yeah? And any two of those vectors, if we use an X gate on them, will not change, so we will have the same as a result. Okay, so that was the first gate, the X gate. So now maybe let's move on to... Okay, maybe now I will introduce a new gate, which is called an S gate. S gate. And an S gate looks as follows. So here we have 1. So here nothing will be like changed. Here we have 0 and 0. And in the lower right corner, we will have I. Or in other words, we will have 1, 0, 0, e to the power of I times pi divided by 2. And here it is kind of tricky to guess what vector do we need. So when we apply the S gate, the final state won't change. So let's again draw some circles. Yeah, so we have here the real part, we have the imaginary part, and here we have cat 0 and cat 1. And what does this gate tells us? So first of all, because on the anti-diagonal we have zeros, here nothing will change. Yeah, in this part nothing will change. no change, yeah. And here there will be a rotation performed. By what angle? Well, by pi times 2. Sorry, pi divided by 2. So a following rotation, yeah? And now, if I ask you, what vector do we need so that the S-gate, when we apply the S-gate, the state does not change? And here, the answer is kind of, I would say, pretty easy, but at the same, like you need to, it kind of test whether you understand like the basic of quantum computing, because those states are ket0 and ket1. Because if we perform here basically a rotation, then for any local phase, something will change in this local phase. But for states ket0 and ket1, like you kind of don't have this local phase, yeah, because it's like without the meaning, like you already have 0 and 1, and adding any kind of local phase won't change anything. So it's kind of important to understand that basically those two basic states, yeah, if you apply something like Z gate, you apply the S gate, or we learn in a few minutes T gate, nothing will change. Yeah? So if you have a quantum operator that have zeros on the anti-diagonal, and it only affects the local phase, which the number in this corner tells you about, then the answer should be one of those two vectors, so our computational basis state. Okay, so I talked about the S state, S gate. Now let's move to the T gate. So a T gate is defined as follows. We again have one in the left upper corner, zeros on the anti-diagonal. And here we will have e to the power of I divided by 4 and of course times 5. Okay, so it tells us to rotate by pi divided by 4, and of course it only affects the local phase, so it does not affect the probabilities when measured, so the amplitudes. So it might be like this kind of rotation, it might be this kind of rotation, it might be such rotation, yeah? So pi divided by 4, so half of a quarter circle. And I'm not sure whether you noticed something, but if you raise the T gate, this operator, this matrix, to the second power, you will get an S gate. So now let's prove it. 1, 0, and 0 into the power of 4. 1, 0, 0, e to the power of I times pi divided by 4. Here that's convenience, yeah. So as the output here we have 1 times 1 plus 0 times 0, it is 1. Here we have 0 times 1 plus something times 0 is still 0. Here we have like exactly the same because this matrix is symmetrical. And here we have 0 times 0 plus e to the power of I times pi divided by 4 squared, basically, yeah? So we can write this as e to the power of I times pi, and here we have like divided by 4 times 2, because we have it's squared, yeah? So we can write it as follows, which is equal to the S gate, yeah? So basically it all makes sense because S gate, we interpret it as rotation by pi divided by 2. And if we apply the T gate twice, we will rotate by pi divided by 2. So it's all consistent. And sometimes you will see there is a different notation for T gate. T gate is sometimes also called the square root of S. Yes, so it's like a kind of like a reverse thinking here, yeah? And sometimes S gate is also noted as P gate, so phase gate. So this is basically a notation thing, yeah? Different notation. And now let's think about the Z gate that I mentioned at the beginning. And we see that if we rotate by 45 degrees, so pi divided by 4 twice, so we basically use a T gate twice, then we receive an S gate, which is basically a rotation by pi divided by 2. But if we apply S gate twice, then we will rotate by pi divided by 2 twice, which will be equal to one single rotation by the angle of pi. So let's me draw it. We have here real part, we have here imaginary part, yeah. And let's say that we are here and I perform the first rotation using S gate, and then I perform the second rotation using S gate. So here I have two rotations by pi divided by 2, yeah? Okay, pi divided by 2, and here we also have pi divided by 2. And so now, let's again calculate the S squared and see what we will get. So we have S squared, which is 1, 0, 0, e to the power of I times pi divided by 2 squared. And from the procedure that we calculated T squared with, let's calculate S squared quicker. So we have here 1, 0, and 0. And here we will have e to the power of I times pi. And e to the power of I times pi, yes, e to the power of I times pi is equal to -1. So here we get the Z gate, yeah? So it comes together pretty nice. And so now let's check what we will obtain if we calculate the Z squared, yeah? So now I believe it should be a bit quicker. So we get like -1 squared. And of course, we have here like 1, 0, 0, and -1 squared is just a 1. So we receive an identity matrix here, yeah? And this is pretty logical, I think, because if you draw how Z-gates acts, it will be like no change, yeah? So we have the real part, we have the imaginary part, and if we say, let's start, let's say here, and we draw how the Z-gates would affect such a vector, yeah, such a qubit, then when we apply the Z-gate for the first time, we will perform a rotation by pi, which is kind of consistent with this notation with how we can write the Z-gate another way. And if we apply it for the second time, we will, of course, also rotate by pi, which means that we in total rotated by 2 pi, which basically changes nothing because it's a whole circle. So it like kind of proves that if you apply the Z gate twice, you get an identity matrix. And as a side note, like it's not the part of this course, I can tell you that the Z gate is very often used to kind of sustain the qubits, because if you execute your code on a real quantum hardware, the fact is that the qubit does not like to stay unaffected, which means there is a big problem with noise. You have like a single qubit waiting for the operators acting on other qubit to finish, yeah? So very often the Z gate is used twice just to kind of keep the qubit involved, yeah, entertained or something like that, yeah. So it's very often used. Just if you apply some gate twice and it gives you identity gate as the output, then it can be used to mitigate errors. And the Z gate is also used, like you can also use the Hadamard gate or the Y gate, but usually this is the Z gate that is used because it's perceived to be the simplest one. Okay. So we have one very important thing done. Okay, and when it comes to notation, I should also write here that the S gate is sometimes also called the square root of Z, yeah? So in the similar manner that we can write the T gate as a square root of S gate, we can also write the S gate as a square root of Z gate. But however, don't write the Z gate as a square root of pi, because it's like it's like not true in this context. Okay. So we have the Z gate, and the Z gate, as I have already presented to you when it comes to S gate, the Z gate, when applied to the qubit, won't change the state of this qubit only if this qubit is in a state ket0 or ket1. So like this whole family of gates that perform a change in a local phase without changing the output probability, so this amplitudes in this part, have this thing in common, that for them to be indifferent for qubits, when you apply them on those qubits, those qubits need to be in state ket0 or ket1. So those gates includes S gate, T gate, Z gate, of course like identity gate, but it's like kind of trivial because it won't change any state, but it also like meets this criteria for changing only the local phase. It changes it by nothing, but it also like kind of meets this criteria. So the pattern is kept. And okay, so we have the X gate that's indifferent to the qubit if it's in the following state. So pi divided by 4 when it comes to this amplitude part. So we have this cosine of pi divided by 4 and sine of pi divided by 4. And here we have a whole axis. So you can be anywhere on this axis, but because we have a circle like this, there are 2 points. But you can see that they're lying on this real axis precisely. We also have the Z gate that is indifferent only if we are like in one of those 2 places, in one of those 2 states, and then this local phase part does not matter for the Z gate. So we have X gate, we have Z gate. So it's time to introduce a Y gate, yeah? And this will be the last of the three Pauli matrices, or the last of the three Pauli operators. And it is represented as follows. So we have this time zeros on the diagonal, so similar to the X gate, and minus I in the upper right corner and I in the lower left corner. So now let's think what will the state look like if we want to apply the Y gate on it and nothing will happen, yeah? So here you can analyze this anti-diagonal and maybe with some help when it comes to like finding some analogous with the X gate, guess to which state it won't affect, yeah? So it will be similarly pi divided by 4 in our trigonometric functions. And when it comes to the local phase part, when we have this real part and we have imaginary part, yes? So for X gate, we have this horizontal line, this horizontal axis or real axis. And here we will have this imaginary axis, yeah? So here will be this part. So this will be like, let's so they will be those two states that are depicted here will look as follows. So we will have here cosine of pi divided by 4, and here sine of pi divided by 4, which is of course square root of 2 divided by 2. And here, so now let's focus on this part. We would have here simply I, or in other words, e to the power of I times pi divided by 2, because we have here this angle pi divided by 2. And another vector where we can use the y-gate and nothing will change is of course the cosine of pi divided by 4 and minus I of sine divided by 4. So those are like those two states that are depicted here. And so let me name those two states. And in other words, if we apply the y-gate on them, yeah, we will get again the same state. Okay. And same applies here, yeah. And if you are like, let's say, more advanced in mathematics, in linear algebra, you should also know another tool that will help you to determine what this vector looks like if you are given a matrix. And I will tell more about it during the next lecture. However, with those methods that I have shown in this way of thinking, you should be able to guess those vectors by yourself, but there is also another tool called the eigenvectors and eigenvalues. And then if you have a matrix U and you have some eigenvector, we call this eigenvector, let's call it W, then if you have some scalar lambda times the vector W, yeah? So this is basically a definition of eigenvector. It's an eigenvector, yeah. And this is an eigenstate, yeah? Eigenstate. And I will talk about more it during the next lecture, but here like I give you some, I would like to give you some intuition to think about those eigenvectors and eigenstates, yeah? And I can also say that those eigenstates will have their modulus equal to 1 because we need still a valid quantum state, yeah? Okay, let me see if there are any questions. Okay, no questions so far. Okay, so we are doing good when it comes to timing. And
There's
okay,
actually
and
one,
there's also
Shamek, there's actually one question from Miron. It has just appeared. Uh, I'm not sure which
okay. Didn't you
about
mean
it, but
eigen?
didn't you mean to
I'm
say
not
again?
sure.
At which point, right?
Eigen.
Because
Yes, yes. Sorry. Here is an eigen
yeah, there's
value. Yeah.
similar words, so there
Yes,
could
yes.
have been
Sorry.
a mismatch, but
Good point. Yeah. Eigen value. And my mistake comes from the fact that sometimes in quantum computing we call this eigenvector an eigenstate, yeah, because a vector represents a state. So here's my okay, so it's my mistake. Okay, so before we move to some coding session, before we move to Circ, one more thing I would like to mention is the Hermitian conjugate of the matrix. So if you have some unitary matrix, if you have some quantum gate, you can apply a Hermitian conjugate, which is sometimes called denoted as dagger. So we have dagger that like a kind of knife, but because if you open a Jupyter notebook, maybe it will look more like a dagger, but here like we kind of depict it with a cross. And what it does, um, so maybe I will write it down as Z1, Z2, Z3, and Z4. So we have some matrix, yeah, and we want to compute this Hermitian conjugate. And what it does, so the first thing it does, it transposes the matrix, but also you need to compute the conjugate of the complex numbers that are inside this matrix. So yeah, so we will receive something like this. And here, because it also transposes the matrix, because here 3, and here we have 2. And here we have, of course, 4, yeah. And sometimes it is also denoted as SDG, or more often I would believe it's like DG. And you can interpret it if you have some rotation as a rotation in a different direction, yeah? So if we have this S gate, yeah? We have here also, we have here S gate here. So at the end, if we have, okay, dobra, I will copy it. Okay. And I want to compute the Hermitian conjugate. Then I need to transpose, but because we have here nothing on the anti-diagonal, there is like nothing to transpose. And compute the, I write this down for the sake of readability. Here we need to compute the conjugate of this number, but we know that this is e to the power of I times pi divided by 2 is equal to phi just I. So the conjugate of I, maybe I'll write something like this, maybe it does not look pretty. It's minus I, yeah? because as you may remember, like if we have some number which is represented, some complex number represented in that way, then if we have its conjugate, then we have a times a minus b times e. So this imaginary part is has a changed sign, and here this a in this case is equal to 0, and b is equal to 1. So after conjugation, it's equal to -1. Yeah. So here we will receive minus I, or in other words, I can also write it. It will become 3 pi divided by 2, or also in other words, minus I times pi divided by 2, yeah? So we are doing a rotation, but in the opposite direction, yeah? We started with I to the power of I times pi divided by 2, and now we have a minus sign, yeah? So this is another interpretation of a Hermitian conjugate of a matrix. Okay, so I will finish with those new operators right now, and now I will switch to Circ. Mm, okay. Okay, now you should be able to see empty Jupyter notebook. If anyone could confirm, you can see.
Yes.
Yes.
Okay, thanks. Okay, so at the very beginning, I would like to compare Qiskit and Circ. So you will have some kind of a comparison. And we assume that you know basics of Qiskit from QBronze. And during this course, like in the beginning, you can see in the note there is some Qiskit, but over time we will switch to Circ. And now I will try to teach you some basic codes in Circ by making some comparisons to Qiskit where I believe it might be necessary to help you to understand. So first of all, in Qiskit, of course, the first thing like we want to do is to initialize a register. Registers, and in Qiskit we were importing them, of course, from Qiskit, and we had quantum register, classical register, and then we have also a quantum circuit, yeah? So good, so let's check if there is no typo. Okay. And then if we want to declare a quantum register, we needed to use the quantum register object. Quantum register. And in the parentheses, we give the number of qubits that we want to use in our quantum register. And of course, we also need a classical register if you want to do some measurement. So classical register. Okay, there is no typo. In Circ, we basically need to import, let's say, just Circ, and then we create something which is called a list of qubits. So let's declare it. Okay. Circ line qubit dot range. Okay, so it works. So here I could, of course, import line qubit directly from Circ by doing something like this. From Circ import line qubit, but I will stick to the convention used in our Jupyter notebooks And I will like, if there is any object used from circ, I will of course write circ.distinct, yeah? And here, instead of quantum registers, we use line qubit objects, yeah? So you can kind of understand this as a similar thing. And then we use the range method that is defined without a line qubit, yeah? So here we defined a quantum register with 4 qubits. So now let's initialize a circuit. Circuit. And in Qiskit, let's name it Qiskit circuit. We need to use the quantum circuit object. And then tell this quantum circuit object about the quantum registers and classical registers, yeah? So there will be quantum register and classical register. And we can give there, I believe, like maybe not as many as we want, but many, both quantum and classical registers. We can pass here like 3 quantum registers and 1 classical register and so on, yeah? But here we are passing 1 quantum and 1 classical register. So let's declare it. And in circ, we need to use circuit object. So let's write it, circuit. From circ, we get simply a circuit object. And here we don't need to pass anything here. Here the construction is slightly different. Okay, so we have registers declared, we have a circuit declared. And one important thing is that in circ, you don't need to declare the classical register. Of course, there are some methods, sometimes they might be useful, but you don't need to declare them. Okay, so now let's move on to some example gates. So in Qiskit, we apply gates circuit using predefined methods. So inside a quantum circuit object, there is a predefined set of gates, yeah, and they are defined as methods. So something that acts on this circuit. And for example, if you have X gate, there is an X method inside the quantum circuit object. And now, as an argument for this function, for this method, we need to tell on which register we want to act and on which qubit inside that register. So let's write this down. I want to act on the quantum register named QREC, and I want to act on the third qubit, so the qubit number 2, because we are counting from 0. Okay, so no error. Then let's say we also can apply the Z gate. And let's apply the Hadamard gate, but on the qubit, on the last qubit, so the qubit number 3. And then maybe let's also apply one multi-qubit gate. So let it be a controlled NOT gate. So it will be Cx, and the first part will be the first argument will be the qubit that acts as a controller. And the second qubit will be the target. So the second argument will be the target. So here I will, let's say, want the qubit number 0 to be the target. So quantum register and qubit number 0. And now let's draw this circuit. So we can use it. The draw method. Simple one. Yeah. I didn't close the parentheses somewhere. The quantum circuits. Okay, I see. Yes, so this is, you can see it looks as it looks. So now let's do a similar thing in circ. And here, the quantum gates are defined as objects that are not functions. Yeah, so they are defined as separate instances that are not defined inside a quantum circuit. Yeah, so there won't be a syntax where we have quantum circuit dot gate. Instead, we will use the append method. And if you know the basics of Python, where you use the list, you can add another element to the list using append method, and the circ follows a similar convention. So we will be appending new gates to our circuit. And for that, first of all, if you want to use some predefined gates, we need to import them separately. So let's say I will import X, Z, Hadamard, control not, maybe control Z, maybe swap, that I will talk about later, and double controlled Xgate. And now let's, in a similar manner, apply Xgate to the qubit number 2, so the third qubit. So now we refer to our circuit in circuit. We use append method that you can know from the list, and then we tell what gate we want to use, so it will be Xgate. Then we open a parenthesis and tell on which qubit we want to act. Yeah, so we want to act on a qubit from a QList, so the quantum register, and on a qubit number 2. Okay, no errors, great. And as you can see in circ, we don't need to tell the circuit that the QList is part of the circuit, yeah? And this quantum register, this QList, will be added automatically to the circuit if we use on this circuit some gate that acts on this register. Yeah. So basically, this quantum register, or rather, I would say the qubit from this quantum register, is added to the circuit here. So, and the advantage of that, as far as I know, is that it makes the objects created, so the circuits created as objects in Python, to weight less. So it's more memory saving, yeah, for our computers. So now let's apply the Z gate in a similar manner. I will just copy it to make it faster. And the syntax is kind of identical to the X gate. Then let's apply the Hadamard gate, but on qubit number 3. And then let's apply the controlled X gate. And here the syntax is also very similar. 0. Okay. Okay, no error so far. And now let's print our circuit. And here, to print the circuit, to draw the circuit, you simply use the print function that I hope you know very well. Yes, so it looks like this. And if you compare it like here, the first thing to notice is that we have 0, 2, 3. And this is because we did not act on the qubit number 1 from this register, yeah, we declared, which means that if it's not used, it is not shown, it is not included, yeah. So it's kind of memory saving again. Well, maybe, of course, you also don't see here classical register. And here it may be problematic, but all the control gates have here like this sign, yeah. And if we use the Z gate, control Z gate, it's very easy to mismatch the notation, but I believe that there will be some examples later, or at least in the Jupyter notebook. Yeah, but this is like the way it is drawn. It's not something to be fear of. Yeah. And okay, so let me show you some more features that are in Circ that will make your programming easier. So if we want to apply some kind of gate, let's say Hadamard gate, which is a starting part of a lot of quantum algorithms. If you want to apply a Hadamard gate, we can use on each method. So let me show you. We have our circuit. Um, circuit. Of course, we use append method. And then we want to apply Hadamard, but on each of the qubits from our quantum register for our quantum list from our line qubits. Yeah. So here we can use on each method. And then we need to pass the list of those qubits, but we need to unpack them. Yes. So I hope that you are familiar with this asterisk sign, what it does. But if not, let me show you. So let's say that we have such a list. And if I want to unpack it, yes, now you see that you have three separate entities, 1, 2, and 3. But without asterisks, you have a list of 1, 2, and 3. And it is because this on each function does not accept a list. You can't pass a list. However, you can pass a lot of numbers. So a bunch of numbers, a bunch of other arguments, a bunch of other objects, but not a list. Yeah. So you need to pass something that is a qubit, not a register. But because a register consists of qubits, you can unpack it, use it asterisk, so it will work. Okay, so now let's print it, the circuit, one more time. Print. So as you can see, Hadamard gate was applied to each of our qubits. Yeah. So we have here the qubit number 0, we have here number 1, we have here number 2, and with number 3, I believe I run something twice. Okay, that makes sense. Okay, another thing I would like to tell you, and I really like Silk for that, is using a controlled by. Because in Qiskit, you need to count which qubit is a control qubit, which one is a target qubit, and so on and so on. And sometimes you want to have like 2 control qubits and 1 target qubit. Sometimes you want to have 1 control qubit and 2 target qubits. And in Circ, you can very easily tell which one is which one. So let's say that I have our circuit again, the circuit. Of course, we use the append. And let's say that I want to apply a Hadamard gate on qubit number 0. So Q list, there should be no parentheses. We have Q list 0. And then we apply controlled by. And here we also need to pass the qubits, but we can't pass a whole list. Like we need to unpack it, so we need an asterisk, and then we refer to our list of qubits. But because here the qubit number 0 is a target qubit, and we want, let's say, other qubits to be control qubits, yeah? So we need to refer to them in a following way, yeah? So here I refer to all the qubits except the first one, yeah? And I have to input because I believe I forgot about the parentheses here. So let's print it one more time. Okay, yes, as you can see here, we have here the Hadamard gate that is controlled by all the other 3 qubits. So I believe it's a pretty nice feature. Okay, another thing is that you can declare your own operators, and I still quite easy. So let's define an operator that is a square root of X matrix. Yeah, we were talking about Z, S, and T matrix. Let's say now we will switch to X matrix. So let's say that our root X is equal to X to the power of 1 divided by 2 or 0.5. And we want to append it to our circuit. Dot append. So we can now refer directly to our root X gate. And let's say I want to apply it to the qubit number 1. Here is 1. It should work just fine. Let's print it one more time. Yes, so you can even see here that here is this like nice notation that depicts what our gate does. Okay, so far so good. So we talked about the gate. So now let's move to executing our circuit and doing some measurements. So in Qiskit, as you can remember, I hope, we have our Qiskit circuit, and to measure, you simply need to use the measure method. And as the first argument, we pass the quantum register we want to measure, and as the second, the classical one, where we want to map the output of our circuit. Okay, and in circ, so first of here we need to import the measure object. So from circ, import measure. And here we will also append this measure operation, circuit dot append measure, right? Simply. And now, as the first argument, we need to pass what qubits we want to measure. And here again, we can't pass a whole register, we can't pass a list. We need to pass all the qubits, but in separate entities. So we again need to unpack our qubits. And the nice part is that you can like still refer that to one qubit, yeah, if you want, but we will come to that later. And because we want to obtain the result of measurement, we use the result. So this is kind of similar to using different types of backends or simulators in Qiskit, but I will show you more in a minute. So let's measure it, and let's also print our circuit in circ one more time. Maybe the one in Qiskit too, okay. Yes, let's draw. Yeah, so here we have those measurements, yeah? And here we also have those measurements. Okay. And now we need to, in circ, we need to declare a simulator. Okay, so I will declare a simulator as S. It will be circ.simulator. You can, of course, import simulator directly. Okay, so if you perform many operations on a single circuit, so one time you just run the circuit to get the measurement output, or the other operation might be that you want the state vector. For all of that, you need only one simulator, yeah? And now let us collect those samples after measuring and running our circuit, yeah? So let's declare a variable samples, and now we need to use run method on our simulator. And now we need to tell the simulator what we want to run, what we want to simulate. Well, we want to simulate, we want to run our circuit that we created in Circ. So this one specifically. And then we can also tell how many times we want to run the circuit. Yeah, so let's say I will do 10 repetitions. Okay. So let's run it. And now let's print the results. And as you can see, it gave us the results as a bit strings, but they are kind of hard to read. So now let's make them more readable. You can use the histogram method with key without. Okay, so we get some numbers, but how to read them? So, first of all, you need to remember how decimal is converted to binary. And maybe I will just do one repetition to make it clear. So here we get the output 2. And it means that we can write it as 0 plus 2 plus 0 plus 0. And here this is because maybe I don't have one note here, but you need to remember about this method of notation where you have like, I will write kind of a pseudocode, like you have like 2 to the power of 0 plus q1 times 2 to the power of 1, q2 times power of 2. So here is some kind of a pseudocode, yeah? So if we measure some qubit and it appears to be 0, this part is skipped, yeah? And if it's 1, it is not skipped. So here, if we have number 2, if we convert it from a decimal to binary, we will get something like this, yeah? So it will be 0, 0, 1, 0. And here maybe I should write it in a reverse order because this one corresponds to this part, yeah? Okay, so maybe I will I have here a sample code ready for converting this counting from decimal to binary, so the way it is shown in Qiskit. So this function you will also find in your notebook. And here we use the fold func, which causes the result to be shown in another way, yeah? So let's write it down. So as you can see, here we have this number 2 written in binary. So now let's do some more repetition. Let's say 5. So here we have number 7 twice, number 8 once, number 4 once, number 5 also once. And if you want to express those numbers like 6, 8, 4, and 5 in binary, we can use this part of code where we have this 7 expressed as binary, we have this 8 expressed as binary, we have this 4 expressed as binary, and so on and so on. Okay. Another nice thing. I will check if there's another important thing. Okay, so maybe I will wrap up this part of converting from binary to decimal. So to understand the result in this decimal form, you need to raise the index of a qubit to some power of 2, but in a reverse order it represents, and then sum it, yeah? Because if let me get some very simple circuit. So I will copy some of the codes. Here, Q list number 2 and circuit number 2. What's the declaration? Declaration by truth. And then I apply an X gate to the first qubit, qubit 2. Let me print it. Okay, I see. I have this, so I have here only an X gate. And for the second qubit, let me just add a Z gate. So it will be kind of an identity gate, yeah? Yes, so we have here X gate, we change the state of the qubit number 0, and applying the Z gate twice does not change anything. So now let us run this circuit. So samples 2, let's run the circuit number 2. And one repetition will be enough because it should always give us the same result. Then print those samples. I have no measurement. Okay. So now it makes sense. So here, the qubit number 0 is in the state this is 0, but what I want to show you is that if you want to interpret those, if you want to get the exponents from the number of qubit, you need to count it in the reverse order, yeah? So here you have this this qubit is it gives you 2 to the power of 1, and this gives you 2 to the power of 0. But before here we measured 0, then it gives you nothing, okay? Okay, so let's move to another feature. So, let us investigate individual runs. So let's move back to our first circuit. And if we refer to our samples by using the measurements attribute, measurements, here we need to refer to the results object in this dictionary. So maybe something like this. Okay. And what is shown here that we have here those 5 repetitions, and we have an array of 5 elements of 5 sub-arrays. And here, every array corresponds to the result of an individual run. So it kind of lists, it breaks down this dictionary to the individual runs. Yeah. So this counts, those counts are basically an aggregation of this array where you are shown the results of individual runs. Another thing that we can do, we can also do it in Qiskit, but here we are using Circ, is that we can print the unitary matrix that represents the whole circuit. So now let's print, we can use the print and then circuit dot circuit unitary function used on our circuit. Circuit. Typo again. Okay, and this is a matrix. This is a giant matrix when we are given a unitary matrix that represents each of the runs also. So maybe to show you it better, how it would look like. So let's say you have here. So you can also print the gate itself. Oh, that's what I meant. So we can print here the gate itself in a unitary form and maybe to do some example. So maybe I will come back second circuit where we have only one repetition here. And yes, so this is this tells us how this one circuit would look like if we put everything in a one matrix. Yeah, because if you have those unitary matrices, we can like square them to be the only one matrix. Yeah. Okay. Okay, so before I move on to discussing the block sphere, let me do the last example in C, okay? So let's say I have 3 qubits. I want to have 3 qubits. So I need our line qubit object, so kind of a register. We use the range. Then we create our circuit. Circuit circuit 2 equal to circuit. And we need also a simulator, yeah? Circ simulator. And now I want to use the Hadamard gate on the first qubit, so the qubit with the index 0. So let me copy it to be a little bit faster. Append Hadamard gate on a qubit from this CQ list. And number 0. This will be okay. And now, so maybe I will launch it and print it. So here you can see that there is only one qubit because we haven't acted on others yet. So here is only the qubit number 0 and qubit number 1 and 2 are untouched, so they are not displayed. So now let's append the Hadamard gate one more time to this qubit. And maybe let's append 2 X gates to the other qubits. circuit. Okay, but instead of applying the X gate twice, I will use this on each method, yeah? On each from a list that we need to unpack, ranging from 1 to 3, because 3 is in use because it's exclusive, yeah? Excluded from the last, from our set, yeah? So here we have successfully applied the X gate. We have also the Hadamard gate applied twice. Okay, and one more thing that we can get the state vector. So let's get it. So we have here results equal to as our simulator. We want to simulate our circuit and print it. Okay, so here we have the following information about our simulation. So first of all, there is no measurements. And it also tells us about all the qubits that we are acting here. So we have this line qubit 0, 1, R2, and what state they are in. So maybe I will comment out one of those Hadamard gates, so you will hear superposition here. Yes, we have a superposition, as you can see. And phase of an output vector like this is not relevant at the moment. Okay, so maybe now at a measurement. So I will like comment out this printing, so we won't have a mess. So let me move on and append some measurement. Append, measure, and I want to measure all the qubits. So I will use QS here. And okay, that's okay. And key equal to result. Yes, and here it should be. Okay, and now we can simulate our circuit one more time. So after the measurement, and print the results again, yeah? So we have here no measurements, now we have a measurement, and here is a sample result, of course. Okay, 0, 1, 2, 3. Okay, because we have also here the qubit number 3, because here we use the range, so we have from 0 to 3. So here is also a note that you need to think about it as a range, as you are using it in Python. So maybe if I do something like this, yes, you can see that the last one qubit disappeared because we weren't doing anything on it. Of course, instead we can simply do something like this and do not bother about the last qubit. It was simply unused, so I get rid of it. So here, if you want to declare n qubits inside this range, you need to write n plus 1, yeah? Sorry that I didn't mention it at the beginning, yeah? Because if you simply do it like I did, yeah, so without being explicit when it comes to range, I kind of a mistake, but this was so far it was easy to correct. Okay, so let me check for any comments. And in a moment, I will move on to the Bloch sphere. Here was also a question what brings Cirque, particularly comparing to Qiskit. So first of all, like there are different frameworks, but one thing I believe that is easier is declaring your own math physics, your own unitary operators. The second thing, it is much easier to construct complex controlled gates. Another thing is that I believe while Cirque is lighter, it does not occupy so much memory. Another thing is Qiskit has a kind of a reputation of a library of a framework that changes very frequently. Yeah. And if you were learning QBronze like a year ago, you might have noticed that some things change over time. For example, how you refer to the air simulator, or like how you conduct the measurements, how you do the measurements, how you get the samples out. And Cirque, I believe, is more stable in that matter, I believe. Uh, but also we like when we introduce it here, like we kind of want you to know more than one framework, yeah. So to keep you kind of open-minded to different framework, like because you have Qiskit, you have Cirque, I believe you have also like many other frameworks, yes, that I won't mention today, yeah. Yeah, so yeah, that's correct. So I hope that I answered your question. Oh, there was also a question about azimuthal angle as the local phase. It depends what you mean as the azimuthal angle. Mm, but maybe if I show the blocks here, it will be easier to understand. But the local phase, I mean only this part of a vector where the distance from the ket zero state does not change. So the output probabilities, if measured, won't change. Yeah. So the local phase, I understand that this is the part of a second element of a vector, if you have a single qubit, the second element, and this e to the power of I times something. Yeah? So this part which modulus of is always equal to 1. So that's what I meant by saying local phase. However, if you read some textbooks, uh, you can sometimes see that local phase is referred to like the whole part of the whole second number in the vector. Sorry, I'm not sharing my screen, but that's on purpose. But maybe maybe I will show this now, my screen back. So yeah, share screen. Okay. Okay, you should be able to see my screen now. I believe I have one more question in the meantime. Okay. Are these gates used for error correction? So no, basically I talked about a Z gate as used for error correction, or more kind of preventing an error. So you can use X gate as well. You can use Z gate. You can use Y gate. You can even use Hadamard gate. But in practice, Z gate is used most often because it's simple. Yes, so it is about the simplicity of implementing it on a real quantum hardware. And why those gates are useful? Because you need an operation that applied twice, which is a small number, won't change the state of the qubit. And why we want to apply it? Because, as I said earlier, the qubit does not like to stay unaffected. And if the qubit stays unaffected by any gates for too long, you begin to obtain some noise that you don't want to have. So this is about kind of a decoherence and such things, yeah, that will influence your computational precision negatively. So yes, X gate can be used too, but Z gate is like the most efficient way to do this because of its simplicity. And so Z gate is perceived as a simpler. Yes. And okay. So I hope I answered your question. And I believe we have another course on quantum error correction. I'm not sure which one it was. For sure, it wasn't nickel. I'm not sure, maybe mercury, but I'm not pretty sure. I would need to check. Okay, so let's move on with the topic. So now I would like to tell you a few things about the block sphere. So this is the block sphere. Yeah, I copied it from Wikipedia. And block sphere is another way to visualize your qubit. And the advantage of it over this representation, where we have a circle and a quarter of a circle, is that first of all you have a one row, like a one picture for it. It's like 3D, so it may be like more visually appealing. But there is one thing that I especially like about it, is that it clearly shows that cat 0 and cat 1 have always like irrelevant local phases, yes? Because let's now let me show you what we have here, yeah? Maybe I will like get it on the another screen. So here we have state cat 0 and cat 1, and they lie on the z axis. And here we have an y-axis. And here lies the state, like here. Maybe I will use this red pen. It's equal to cat 0 plus I times cat 1 divided by the square root of 2. So it's an equal superposition, but with a local phase of I. And on the other hand, we will have here the same, but with minus I. Yes? Whoops. And on the x-axis, here we will have like this pretty normal something like here. We will have this normal equal superposition. So with the local phase equal to 1 divided by 2. And on the opposite part of this x line, we will have the same one, but with the opposite sign with respect to the local phase, yeah? And one thing you might notice is that this circle here, this with the dashed line here, nice, it corresponds to the local phase of the state cat 1. And if as you move closer to the state cat 0, like it shrinks, yeah? So if you interpret this cat 0 state as a north pole, if we make some analog to the Earth, you can see that like you can't move west or east on the north pole, yeah? So you can also think about the local phase here, that like you cannot like move around the circle if there is no circle, because there is only a point like this. So a cat 0 is simply like a point on this block sphere, and on Earth a north pole is also a point, so it does not go around the Earth like the equator, yes? and the same applies to state cat 0. One thing for what I don't like the block sphere is look, like between state cat 0 and cat 1, you have an angle of pi, so 180 degrees. But we know that states cat 0 and cat 1 are orthogonal. So it might be kind of misleading, yes? So you need to keep that in mind, that if you have some state, let's say sine of, so it should be cosine here rather, cosine of theta at some angle, let's call it lambda, and here we have sine theta. And then if you want to visualize it's this vector on this sphere, you need to multiply this theta by 2. So you would need here 2 theta for visualization, yeah? So if someone tells you that the angle on the block sphere is, for example, equal to pi divided by 4, you know that actually you need to write it cosine of pi divided by 8. Yes, so be careful whether we are talking about, let's say, normally defined quantum state, or whether we are talking about the angle on the block sphere, yeah? Because here it's actually 90 degrees, yeah? So it's actually pi divided by 2, so it's not pi. 2 for block. And by the way, if you wonder how to spell Bloch, it's after Felix Bloch, the Swiss American physicist. So I believe it's spelled like in German language. Bloch or Bloch. Okay, and now let's move on to the other axis. So we have here x axis and y axis, and here you don't need to change the angle of the local phase, yeah? So here it should be a little bit easier if you interpret the local phase. Yes. Okay, I believe that's it. Let me check if there are any questions. Chat. Okay, here's someone wrote that Z gates correct phase with error. Yes, that's correct. Yeah. So in the current state depicted, the phi is the local phase, right? If phi. Yes, it's exactly as Justin you wrote. It depicts the local phase because I believe here is our projection, and here is our like this line, this x gate, like corresponds to the real axis. Yes, so maybe so this point corresponds to this point. Yes. And here, like we are somewhere like here, so we are rotating towards the y-axis, so we are rotating probably somewhere there. Yes. Okay, and yes, so when it comes to blocks, I believe it's that. And the global phase, yes. So a global phase is, as you can read, is physically indifferent to our quantum state. And if I think about it in terms of Bloch sphere, I interpret it as a rotation of the whole sphere. Yes. So if you rotate, let's say, the Earth by some angle, then the position of the poles won't change. So that's kind of the way I interpret the global phase. So like you turn this whole block sphere around in different direction, but in the end, the position of the axis does not change. Yeah, so that's the way I interpret the global phase. And basically, like we have somewhere like here, like we extracted the global phase, yeah, when we were getting from there to there. Because on the block sphere, you only get a depiction of the local phase by this second element of the vector, yes? So it depicts on the second, the local phase of the second element. And this is really important to remember that the block sphere always tells you that the local phase by the first element of the vector is equal to 1. So it's like it is said that is like the easier way to interpret this kind of it's up to how you organize your notation system. And we have also another question about from Tan. In case of qubit and Q-treat, how degree of complexity will change? I'm not sure what is qubit and Q-treat. What do you mean by qubit and Q-treat? Maybe other people will know. So sorry, but for that question, I cannot answer today. But maybe okay, Q-treat is a clear. Okay, level Q is let me. Oh, I cannot open the chat. Okay. Where is the chat? Okay, oh, now I see it. So I wonder complexity of what? If you are talking about the complexity of a circuit, oh yeah, this is a very good question, like the degree of complexity, because usually we talk about the complexity of a circuit after we have all the operations, yes? So you cannot, like if you talk about the complexity of the circuit, you need also to have operations defined, because the first thing that you need to investigate is the number of qubits you are acting on. And the second thing is like the number of operations. But here's another important thing, and that you should analyze your circuit complexity after transpilation, because here we are talking about different kind of gates. But if you try to launch your code on the real quantum hardware, it will use only 3 gates. And this is pretty important to remember, yes? And there is a procedure called transpilation when all of gates are translated to those 3 gates. It is usually C naught. I'm talking about IBM now. It is like C naught, RY, so rotation about the y-axis, and one other I don't remember which one. So all those matrices, all those operators that you use need to be translated, and only then you can talk about this complexity. Yes, because depending on the method you use of this transpilation, the result might be different. Okay, we have also another question. If we apply z-gate when the block vector at 0, the local phase is 0 or pi. If we apply z-gate at the vector 0, the local phase will be equal to 1. So if we have like z, yes, we will get still z here, and here is the local phase. Yeah, so this is like it's equal to 1. And remember that the block sphere is only a way to visualize your qubit, yes? So you basically, the Z gate here, it will perform the rotation around the Z axis. So perpendicularly to it, not parallelly by it. An X gate or Y gate are perpendicular to this like Z axis, yeah. Okay. No, sorry. The Z gate is perpendicular to the Z axis. Yeah. So it will like if you have this state like here, it will perform the rotation around the Z axis. So here we have the Z axis. So it will do something like this. Yes. Or maybe also the and here like this probably. Yeah. So this is the how a Z gate would react, yes? And I recommend to investigate the Z gate in this form, the local phase in this form. The Z gate local phase should be pi, right? And the Z gates. Um, yes, you are right. Yes, so if you start with cat 0, remember that the local phase won't change. But if you start with basically any other arbitrary state, which is non-trivial, so if it's not cat 0 or cat 1, the Z gate will do exactly as you say. Yes, so it will change this azimuthal angle by pi. I'm not saying that it will be exactly pi, but it will change by pi. So if we have some quantum state, let's say alpha and beta, where alpha and beta are not a part of the set, then we can write. And of course, you can still write this minus if you had this basis state, but then the local phase will still be 1, because as I gave this interpretation of poles, like changing the local phase, if you look at the block sphere, it's like going west or east, yes, on the Earth. And if you are standing at the North Pole, so the state cat 0, then like you can't go west or east, yes? And that's kind of how you should look at it. So even if you write down any local phase, so for example, -1 here, like this minus, you like forget about this, it will be still indifferent to the future computation. Okay. Um, so maybe I will write down why this is also indifferent. So if you have state cat 0 state, yes, and you apply that here, then you get 1 and -0, yeah, which is 0 basically. And if you apply it to cat 1, 0 and 1, you will obtain here -1, where you can extract the global phase and simplify your state. Yes, so this becomes a global phase. Its modulus is equal to 1. Okay, I think we are about to finish the lecture. So maybe I will quickly go through the Jupyter notebooks. I expect you to browse through. And for today, after today's lesson, you will have 2 assignments. After the first lecture, you have one quiz for 10 points, I believe, or 20, I believe. So, but it was basically a quiz, simple. And now you will have a quiz and a coding assignment. And they will be like worth 50% of the grade for today's lecture. Like you will see it in Canvas, how much points you can obtain for each of those assignments. Yes, and quiz assignment will be similar to what you have seen during after the first lecture. While the coding assignment, it will be like you download the Jupyter notebook from the site. There will be a link and URL to download it. Then you will be expected to fill in the gaps in the cells inside this Jupyter notebook. There will be like instructions in comments written, so you don't get lost even if you like forget what I'm talking about. And then you need to re-upload this. Yeah, so there will be I believe, three basic exercises to do using Silk. And during the next lesson, we would start talking about procedures and algorithms. We will start talking about the Fourier transform, which I will explain in theory, and we will have also a bit of coding. Then I will talk further about those eigen vectors and eigenvalues. Then I will talk about quantum phase estimation, which is basically about estimating eigenvalues. And after the third lecture, you would have only a quiz, so similar to like what we have after the first lesson. And then during the fourth lesson, I think I will focus more on coding, like coding this quantum phase estimation. And I will also talk about order finding algorithm, which is a fourth part of the Shor's algorithm. And after the fourth lecture, you will have only coding assignments. Yes. So I really recommend to like learn a bit of Circ and to test yourself, you will have this assignment. And I have a problem, I believe, with sharing my screen when it comes to the list of notebooks. Okay, now it should be fine. Let me share it for a moment. Blah, 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 blah. Okay, we are here. Share. So now you should see the list of notebooks. So A00, it's like a revision. Which I hope you already browsed through. Another part is the complex number. We have it already. C01 we have already. C03 we have briefly discussed it, but if you haven't like browsed through it, I highly recommend to quantum gates. We have it today. About the local phase, I believe most of the information I gave on Monday. State conversion and visualization blocks for operations on the block sphere. It's what we talked about also. This visualization, I believe, is more like something for your convenience. Yes, so not something that you will be tested from, but it's more like giving you more skills when it comes to visualizing your quantum states. And multi-qubit operations, I talked about it briefly when I talked about this controlled by gates. So here it will be also for you, and the Silk introduction, something that I believe, made, but in another form. So everything until D00 can be like examined in the test. Okay, Wojciech wrote that the input circuit is locked, so I believe it should be available in an hour after 9 p.m. Warsaw time. But I will check whether there is something like
Uh,
incorrectly set. Pavel,
Przemek, I can tell you that the quiz is already available. We'll check it. I've already
okay.
started consulting it with our
Hmm.
communication department, okay? So we'll
Okay.
let you know and fix it if
Okay.
needed.
Okay, so I will also maybe answer the other question of Thomas. If we apply z-gate to cat0 twice, and then the local phase will be 2 pi or 0. So uh, maybe I will write it down because I would say that both answers are incorrect, but I will show why. Because this is something I believe a small mistake that I made yesterday, but someone corrected me, luckily. Understand, share. Okay, so a z-gate is a rotation by pi. And if you have some state, and you have here cosine theta and sine theta, and here you have e to the power of I times lambda. So after applying a z-gate, you will get here cosine theta, nothing will change. And here you will get e to the power of I, and here the angle will be lambda plus pi, because this is a rotation by pi. And if we start in some state, maybe not necessarily cat 0, because as I shown you, cat 0 is trivial, and if you have cat 0 or cat 1, you always have a local phase of 1, because here you have 1, 0, and here you will have like 1. So this is cat 0. And for cat 1, you will have here 0, and here will be 1 times 1. And in other words, this 1, maybe I will draw an arrow here, 1 is equal to e times I times 0. However, you can also write it as e to the power of I times 2 pi, or in general, everything that is can be multiplied by 2 pi. And because why? Like, because we are running in circles, yeah? Because like we have a circle here, so we are like, if we rotate by more than 2 pi, like then we can like start from the beginning, because it won't change anything. And local phase is this whole number, yes? So it will be a number between -1 and 1, including imaginary or complex numbers. Yeah? So anything that which modulus of can be equal to 1. And so this is a local phase. And this lambda here is its angle. So the angle of, I will write surely LP, local phase, which can be interpreted as an angle of rotation around this circle or this circle, yes? But beware of this angle theta, because here you like need to multiply it by 2 if you want to visualize it, but only for the if you want to visualize of the blocks here. So it's only a visualization. It's like if you think that the blocks here added some complexity or complicated things, then I would simply like stick to this classical mathematical notations or those two drawings that I were showing you previously. So if you, Thomas, to summarize, if you have cat 0, the local phase, you can say that this is irrelevant, or you can say that this is equal to 1, or you can say that this is equal to e to the power of I times 0, or e to the power of I times 2 pi, and so on and so on, yeah, because it's like angle, so we are running in circles. Okay, that's all for today, I think. If you have any questions, I will be available on Discord, and I think we can stop recording now and end the lesson. I will upload this OneNote. Maybe I will like make small changes to make some things easier to understand. I will also upload the Jupyter notebook I was working with you on. So thank you and have a good night.
Thanks, Przemek. I will now stop recording.